All right, seems to be working. We'll see. All right, Max is hydrated. We're ready. Let me see. I was going to remind everybody of the schedule. How do I, hold on. Okay. Schedule update. You should have seen, that might have been shocking, but you should see feedback to your homework from last week, already graded. I'm up to date. So you should see feedback to that. We are not going to turn in 17.3 homework. We're going to work on that this week. And that will be included on the exam, which we're going to do after class on Thursday. So today we'll do homework questions on 17.3. That would be good because I don't have any 17.4 prepared. But we did have one example yet that we hadn't done from 17.3, so we can do that. We did a couple of them. We did 2 of these here. We did not do the last one, so we can do that. And then we can pull up some 17.4. That'll be fine if we need to. I'm sure we'll find plenty to do. Yeah, and then tomorrow, I'm going to try to work today and get 17.5 videos done. It shouldn't be a super long section. Next week is going to be our heavy lifting, 17.6. Think about line integrals and what a new idea that was, and like it kind of required some careful thought. So if you can imagine integrating along a line, well, what if we have a whole surface and we want to integrate on the surface? That's 17.6, and that's going to be a big one. That might be like 3 videos. So that's going to be our focus next week, and then we're going to do 17.7 and 17.8 are like really, like they're kind of the main point, but because they use surface integrals, we have to spend a lot of time developing 17.6. And 17.7 and 17.8 though are like, it seems like I'm cramming it all in at the end, which is what we're doing. Sorry, it's a global pandemic. But they're like a key theorem, and then we'll do 1 or 2 examples from each. And so they're going to be, it'll be fine. But 17.6 is the big one. That'll be our heavy lifting next week. So what I'd recommend is once you get your exam turned in, I'll hopefully have those 17.6 videos ready by Saturday, so you can start watching them over the weekend and kind of be thinking about those and starting on those. All right, so I think that's our plan. Yeah, and then finals week, we'll have class on Monday, and then we'll release the exam right after class. And you'll have 2 days to work on it. It'll be due on Wednesday. Any schedule-related questions? Course-related questions?
Yeah, wait, so the final exam, is that going to be due Wednesday or Thursday?
Oh, it should be Thursday. Yeah, or it should be Wednesday, I'm sorry. Because the semester ends on Wednesday. I don't know if I can edit. Can I edit this quickly? We'll just put it in there. Yeah, so the semester officially ends on Wednesday. Yeah, fixed. Thank you. And there we go. Final exam due there. There we go. Good fix. All right. Any other schedule-related questions? All right. I'm going to get the homework up. Oh, I need to get the chat window up too. I know we use the chat a lot. All right. So let me get the homework up. Did anyone? I know you were. I don't know if you got to the 17.3. I did not really post them early enough, and I apologize for that. So I don't know if you've gotten to those. Did anyone have any questions that you wanted to ask from? Oh, it was 17.4 that I just posted. Yeah, so 17.3 you should have had. So did anyone have any 17.3 homework questions?
I had a few.
Okay, get us started, Rudy.
Number 23.
All right, so I've got the homework pulling up right now. It's thinking, my cursor is thinking. Where did it go? Why did it not open? There we go, little delay. Okay, there we go. Zoom in a little bit. All right, exercises. And my brain can't hold it in my mind that long. 33 or 23?
23, 2-3.
2-3, 23. So we're looking to find potential functions. All right, and these ones that are 3-dimensional are the one definitely like And they're hard, it's harder when they're three-dimensional. All right, and let's make sure the directions here. Determine whether first of all, determine whether they're conservative. If they're not conservative, then there is no potential function. If they are, then determine the potential function. Okay. So for three-dimensional ones, all of the cross partial derivatives have to be equal. So we're going to, reminder here, we're going to consider this some function f, a function g, and a function h. So we need the partial derivative of f with respect to y. That needs to be equal to the partial derivative of g with respect to x. We need the partial derivative of f with respect to z to be equal to the partial derivative of h with respect to x. And we need the partial derivative of g with respect to z to equal the partial derivative of h with respect to y.
Yeah, I already did that part.
So was it yes for all of those?
Yeah.
Okay, excellent. All right, and so then the key is that f, which is z1x, is the gradient of some function phi, which means it's the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. And that's the foundation of the whole problem right there. So phi x equals z, phi y equals 1, and phi z equals x. And you can go really in any order here. I usually just start with x and work my way down. So I'm going to label that 1. So step 1, if the partial derivative of phi with respect to x, I can't draw a phi today, right? A phi, is equal to z, well, that means that phi itself must be the integral of z dx, or the antiderivative of z dx. Well, that would just be, z here is treated as a constant, so that'd be z times x plus, now I'm integrating with respect to x, so that means there could have been some function here, but that function must have been a function of only y and z. All right, so we've used the fact that the partial derivative of phi with respect to x is z. In fact, you can check that. You can look at that and say, well, what's its partial derivative with respect to x? Oh, it's z. So that's good. Now you need to use the other two, and you can go in any order you want. Most people just go in order, and that's how we did the one in class. They say, well, the partial derivative of phi with respect to y is supposed to be equal to 1. All right, so step 2, partial derivative of phi with respect to y, that'll just be 0, and it'll be whatever the partial derivative of c is with respect to y. And that's supposed to equal 1. So the partial derivative of whatever that c function is with respect to y is equal to 1. Well, that implies then that c of yz must be the antiderivative of 1 dy. Just dy here, because this was a partial derivative with respect to y. And that's just y. But c is a function of y and z, so there could be some other, maybe call it d of z. Right, because the partial derivative with respect to y was just 1 only. So that means there could be a function of z hanging out there. All right, now this tells me that phi is equal to xz plus y plus some function of z. And you can maybe see where we're headed. Now we're going to use step 3 and say, okay, well then phi with respect to z would be x plus whatever d prime of z here. We don't need partial notation because d is a single variable function. It's a function just of z. But we know what phi sub z is, what the partial derivative with respect to z is. It's equal to x. Well, that implies that d prime of z must equal 0. So d must equal some constant.
Wait, okay, I'm a little confused on step 3.
All right, so, oops, sorry, I meant to erase that. Going back up then, what I did is, are you okay with the result from the previous step?
Yes.
Okay, so now I'm going to take its partial derivative with respect to z. So the partial derivative of xz with respect to z would just be x. The partial derivative of y with respect to z would just be 0. And then d is a function of z. So its derivative with respect to z would just be its derivative, d prime.
Okay.
But we know from above that the partial derivative of phi with respect to z is x. It's the z component of our field. Does that make sense now? Is that connection clear?
Yeah, I was just kind of under the impression that we had to do like the integrate all 3 functions.
Yep, you'll notice here, the first one we started with a partial and then we got phi. In the next 2, we take a partial derivative because we want to use the fact that we have these partial derivatives. So we start with taking a partial derivative. Yeah, then again, we took from this one that d prime of z must be 0, which means that d must be a constant. And so there we have our c, our phi. Phi must be equal to xz plus y plus some constant. And you could pick any constant. You could pick 0. So like if you left it off, that's okay.
Okay, got it.
All right, good. All right, you had another one too, Rudy?
Yeah, but if anybody else has any other questions, they can go first. I got quite a few homework questions.
It's all right. Anybody want to jump in, or do you want to let Rudy keep going? It's up to you. You can type in the chat too. I've got that up. I guess it's you, Rudy.
All right, then the next one I had a question on was 39.
All right, using the fundamental theorem for line integrals. This is exactly why it doesn't matter what the c is. All right, let's go over here. All right, so first of all, we're supposed to verify, I feel like I have to make this so small, it's kind of annoying. Verify that the fundamental theorem can be used and then integrate this along. So we better look back at our notes and figure out, hold on, when can you use the fundamental theorem for line integrals? Okay, so here's the key. If your field is the gradient of some phi, in other words, if the field is conservative, then you can use the line integral. You can use the fundamental theorem. So the field has to be conservative in order to use the fundamental theorem of calculus. So that's what we need to check. Okay, so let me scroll down here. So verify the fundamental theorem of calculus, fundamental theorem for line integrals can be used. The question here is the field conservative. We just have a 2D curve, a 2D vector field here, 2x, 2y. And so all we need to do is take the partial derivative of f with respect to y, that's 0. And the partial derivative of g with respect to x, that's 0. Those are equal, so yes. The fundamental theorem for line integrals applies. In other words, what that means is that the field is the gradient of some potential function phi. And the way we're going to do that is instead of taking the line integral of the field dr, we will instead evaluate phi at one endpoint, at the endpoint, second endpoint, and subtract evaluating it at the initial one. So we need to figure out what is our phi, and then we also need to figure out the a and b here. Oh, we have the a and b. They're given to us. In fact, we could say, so this b, this actually, I think I'm using the wrong notation here. We used capital B and capital A to represent points. 3, 4, and 0, 1. It's the line integral that goes from t equal a to t equal b. Right? The line integral goes from t equal a to t equal b, but our phi function, our potential function, is a function of x and y, and we evaluate it at points. So 1, we will need to find phi, and then 2, then we'll use the fundamental theorem of, I always want to say calculus, of line integrals. I keep saying it, but it's so weird teaching Calc 1 and this at the same time, because like we're literally this week, going to be working on the fundamental theorem of calculus for my Calc 1 students. It's the same thing. You know, that's when you do your integral from a to b of the derivative, and you say, oh, it's the antiderivative at b minus the antiderivative at a. It's like the same thing. Okay, Rudy, did you make any progress with finding phi, or is that where you got stuck on, or like what is your question about this one? I guess I should clarify that.
Well, I was trying to, I guess I didn't read the question properly because I was trying to parameterize everything, and so that probably made things more complicated than they needed to be.
Right, now you could, here's the thing, because the field is conservative, you can in fact find any curve between these two and use that curve and evaluate the line integral. But maybe your parameterization made it hard, is kind of what you're hinting at, maybe. But
yeah, I think I kind of screwed up with my parameterized.
Yeah, I would just do a line. This looks like y equals x plus 1 to me. Slope of 1, y-intercept of 1. So then parameterized, it would just be t and t plus 1. And you could use that. And then t would go from 0 to 3. So this would be one, like, we could have a question like this on the test. Right? This is a perfect example of something that we could have on the test. And so if you did the line integral that way, like even if your answer is correct, you wouldn't get the points because you haven't used the fundamental theorem of calculus. So I like your thinking there, because that's what we were doing in the earlier sections. It's like, oh, find a curve, parameterize it, and then use that to do the line integral. Like that makes sense. But here we're going to do it a little bit differently. So let's go ahead, let's try to find phi. The key here is that our vector field, which is 2x, 2y, is the gradient of some phi, and it's just two-dimensional here, so that's phi with respect to x and phi with respect to y. So the partial derivative of phi with respect to x is 2x, and the partial derivative of phi with respect to y is 2y. Oh, I feel like we could just write this right now. I bet you could. I bet you could write phi right now. You probably don't even need to do any work. I'm going to do the work, but I'm interested. You could try it if you want, kind of write it down. But if the partial derivative of phi with respect to x is 2x, phi must be the antiderivative of 2x dx, which would be x squared, but there could be some function of y hiding out here. We'll call it like h of y, some function of y. Right, because we were taking the partial derivative with respect to x. So phi is x squared plus some function of y. Well, let's take its partial derivative with respect to y. So phi y will be, well, h prime of y, because the x squared just becomes 0. But we know what phi y is. it's 2y. So that implies that h must be the antiderivative of 2y dy, which would be y squared plus a constant. So that means phi must be equal to x squared plus h of y, which is y squared, plus maybe a constant. Did anybody have that? Did you already see the x squared plus y squared? I don't know if you saw that up above. You can kind of see if the partial derivative with respect to x is 2x, then it must be an x squared. If the partial derivative with respect to y is 2y, there must be a y squared. You can kind of see that ahead of time.
Yeah, I could kind of like figure that out just by looking at it, but I just couldn't figure out how to get there.
Right. Totally. So it's the key is that making that logic, you'll see the progression here is very similar to the progression I did on the previous one. It's the same logical progression every time. And we're not going to collect the 17.3 homework, but I did post a key here, like my solutions for it. So if you want to take a look, you'll see that like I use that same reasoning there. I don't know if we have any. See the logic here? Same reasoning. It's the same process. This one is different. Yeah, those are different. But that number 24 here, I started the wrong problem here, but number 24, it's the same logic there that you do for all of those. All right, I think we can finish now because now we have our phi, and the c doesn't matter because what we're going to do is instead of finding the line integral dr, we are instead just going to evaluate phi at 3, 4 and subtract phi at 0, 1. And the plus c doesn't matter here because it would be in both of those and just subtract out. So the c doesn't matter. So this will just be 3 squared plus 4 squared minus 0 squared plus 1 squared. And that is 25 minus 1. So we get 24. Now I'm interested. Now I kind of want to do it the other way. Just to prove that we get the same thing. So let's do this. So that would be from 0 to 3 of 2x, so 2 times t, and 2y, 2t plus 2, dot product with dr, which will be r prime 1, 1, dt. Okay? This is the old way. This is the line integral, the old way. That would be the integral from 0 to 3, 2t plus 2t plus 2, so 4t plus 2. Doing a lot in my head, not recommended. Okay, also not recommended trying to squeeze all this work in here. 2t squared plus 2t from 0 to 3. I'm getting nervous. Because it should be the same, but I'm getting nervous. Okay, 3 squared is 9 times 2 is 18. Oh, so cool. 2 times 3 is 6, minus 0, 24. Same thing. So we didn't prove. We just verified that the fundamental theorem for line integrals did work here. You don't need to do the line integral. You can instead find a potential function and evaluate the potential function at the two endpoints. Cool. This is something where I've written questions like this before with this theorem, and then also with Green's theorem in 17.4, and then there's two other theorems, Stokes' theorem and the divergence theorem there at the end, where you have two kind of equivalent versions. And a classic question is, not prove, but show that the fundamental theorem for line integrals applies here by computing both integrals. Compute the line integral, see what you get, compute the difference in the potential function, see what you get, and show that they're equal. And so it's a good question. But it's a big point question because there's a lot to do there and it takes a lot of time. And so that means you can't have 15 questions here. You have maybe 7, and one of them is like 15 points because you have to like Well, first of all, I have to prove the fundamental theorem for line integrals works. So I have to prove it's conservative. Then I have to find phi, evaluate phi at the endpoints. I have to parameterize a curve. I have to find the line, and there's a lot of stuff in there. So you'll get there's lots of points that need to be accrued in there, but it's a good way to really show that you understand these theorems. So I would say when we get to, like for this test, it would be just, this is the only theorem, but either this test with this theorem or on the final for one of those other theorems, you will see a question that says, show that this theorem works, basically, where you have to do like all parts of it and show that they're all equal, show that the two sides are equal.
For a question like that, would you throw in parts, or would you just, just throw up the question and then we would have to work through it?
Yeah, you'd have to work through it. And so it's really important to keep good notes about, here's the theorem on your formula sheet. You've got the theorem clearly labeled. You've written down, when does this theorem apply? And then you just kind of work separately. Like you do the line integral over here, you'd find the phi over here, and you'd kind of, I don't know, there might be some parts where I would say, like, think about this question. You could have an A, verify the fundamental theorem of line integrals can be used. B, find a potential function. C, show, like find the line integral. And then D, like show that the theorem is true or something like that. But I think I really would prefer a more general one where you would know, well, in order to show it's true, I have to do all of those things. So I could see it either way. I could see a parts one where it's kind of broken down for you, but that's less insightful for me in terms of insightful into how much you know. That's less insightful than a broader one that simply just says, like, verify the fundamental theorem for line integrals works and show that it's true for this function, for this particular example. Rudy, I know we did some extra stuff here. I think you were probably fine with it, but just to clarify, do you have what you need here?
Yeah, pretty much everything that I was had a question on just got answered on here, so
Okay.
that cleared things
So
up.
do you think that cleared up? Like, do you have more, or?
I do have one more just because this one's in 3 dimensions.
Sure.
Number 53.
Ooh, this is a good one. I like this one. Does anybody know why I like it? Yeah, too small there, sorry. Anybody know why I like this question? It gets at what we were just talking about for Max's question about what I would ask.
It says use a method of your choice.
Right?
Like
No. So this is like, you gotta decide, okay, it's given me a path, right? So I could just do the line integral.
Yeah, that's what I tried doing, but I don't know where I went wrong with it, but
Well,
it was completely off.
it might be that you get an integral that you're like, I do not want to do this integral. And so maybe what we should do instead is use the fundamental theorem of calculus and find a phi, right? So let's set up the integral first. Oh.
It's a long one.
It's also a closed line integral.
Oh, that's what that means.
Yeah, what that means is, that means that the path that you're integrating over loops around. I have a sneaky suspicion. Sneaky suspicion. I'm just checking in my head right now. Oh boy. Oh. Did you write down what the answer is, Rudy? Don't say it out loud, but do you know what it is?
No, I don't know what it is.
Okay, all right. So, I'm sorry. I'm having a hard time not giving away the punchline. Okay, so let's set up the line integral. To your point, it is not going to be pretty. 0 to 2 pi. The field is 2x, so times 3 cosine t, y times 4 cosine t plus z squared, 25 sine squared t, comma, x squared, 9 cosine squared t, 2xz, 2 times 3 cosine t times 5 sine t, dot product with r prime, -3 sine t, -4 sine t, 5 cosine t dt. I'm tired just looking at that.
Yeah, already I'm seeing some mistakes I made when writing this down because I forgot the z squared on the first part.
Yeah, there is a lot to keep track of here. I would look at that and be like, nah, no, no.
Some stuff, yeah, some
You need
stuff
to
does
check
like,
that. Yeah,
some stuff does eliminate and it like looks nicer, but
right. Daniel has asked a very important question, which is very relevant to you in the chat right now. So
oh yeah,
I want everyone to take a second and read Daniel's question. Then I want you to think, like, let's take 30 seconds and tell yourself, why is that such an important question? Ask yourself, why is that such an important question? Okay, so 30 seconds, 30 seconds. I don't have a timer. There's no second hand in my watch, so I can't look at my watch. I'll just count to 30 in my head. Don't say it, don't give it away. And then what I would like you to do is, if you know the answer, you can go and click the yes, the green yes, okay? If you know why that's important, you can go ahead and do the green yes, everybody. I think we talked about that last time, how to do the green yes box. Didn't we talk about that? I think. If you know why that's important, you can go ahead and check the yes. Now, Daniel, I'm assuming your check is the green yes, right? I'm assuming you know why it's a good question, maybe. Well, so far I have two if we count Daniel because he asked the question. So far I have 2 people who know why this is a good question. Anybody else want to check yes? We got 3. Kyle White's got it. Or thinks he has it. Thinks so. Rose, okay. Good. Michael Giannopoulos. Okay, we're getting there. Okay, this is good. All right, I think Daniel, are you comfortable answering? You can either type or unmute yourself. I think it's a good question. I think you should have the honor of answering it. Yes, you're correct. It should equal 0. Oh, so does anyone know why it? Yeah, no, you're right. So you do not need to show that. Here's the reason why. So if you recall, fundamental theorem of calculus, I keep saying calculus. Fundamental theorem of line integrals says you can integrate over your curve f dot dr, and that should equal your potential function at the endpoint minus the potential function at the beginning point. However, if it's a closed curve, what's true about the beginning and ending point?
And that they begin and end at the same point.
Right? A is B, A is E, they're the same point. So if it's closed, you get 0. And it doesn't even matter what phi is. So Daniel, to your point, here's how we should do this question if this was a test question. Because you see, this only applies if the fundamental theorem of line integrals applies. In other words, it only applies if f is conservative. So this is where Daniel said, if we prove that f is conservative and the curve is closed, do we still need to find the potential function? No, but we do need to do that proof. But that's all we need. And we just kind of need to complete our logic. So let me write f again here. It was 2xy plus z squared. Oh, I lost it. X squared and 2xz. Okay, so we have to do these three cross partials. If you recall, it was fy should equal gx, fz should equal hx, and then gy should equal, gz should equal hy. All right, so fy, the partial derivative there would be 2x, and then gx is 2x. Okay, good. So far, so good. Fz would be 2z, and then hx, also 2z. All right, good, good, good. Gz, that makes me nervous, that's 0. And then hy, but it's y though, is also 0. Yes, okay, so here's what you would show. You'd say, therefore, the field f is conservative since C is closed, the integral over C of f dot dr equals 0. Done. And that's why when I was looking at it, initially I was like, I started to get a smile on my face because I'm like, oh, this is conservative. Oh, that means it's closed, so that it's going to be 0. So great insight on that one, Daniel. Good job. So here's the worst part about that. Suppose you didn't recognize that it's a take-home exam. How much time are you going to spend on that line integral at home, where if you had just recognized that it was, or even if you had just tested whether it was conservative and seen, wait, it's conservative, and then, you know, even finding the phi function would be better than doing that integral, I think. So anyway, so great question on that one, Rudy, and good insight again, Daniel, on that. Cool. This is why these theorems we're learning. This fundamental theorem, Green's theorem, and then we're going to do Stokes' theorem and the divergence theorem. We're going to have 4 important theorems. All 3 are similar. They're like 2 different quantities that measure the same thing, and knowing which one to do, in this case, do a line integral or use the potential function, knowing which version to use is really powerful. So, cool. All right. We're still working on homework. Anybody have any additional homework questions? Oh, wait, no, Rudy, this was your question. Are you good on this one?
Yeah, I'm all good on that one. So is it like saying that because it's closed and it's conservative, it's like no work is being done because it ended at the same spot it started?
Yeah, there'd be like no, it'd be like imagine going around and like the potential, like the field is like, say the field is horizontal. So for part of it, the field is pushing you, but then the rest of it, you have to push against it, and so that the net work done is 0.
Okay, got it.
Yeah, yeah. Cool. All right. So any other homework questions?
Okay, I have a question on that one diagram that you just drew.
Uh-huh.
So for the field, what if, let's say on the left side or the right side, there's less like magnitude in the field
Right.
lines,
Right. That's
and it's
really
still
important.
a closed interval.
Right. Then it wouldn't
be zero.
It probably would not be conservative then.
Okay.
Yeah. Yeah. We can't, it's really hard to graph this one in 3D, but essentially you would need like the net magnitude to be the same on the both sides. If one side has bigger arrows than the other, then it might push you more than you have to go against it on the other side. But you would know because the field wouldn't be conservative. Yeah, that's what will tell you that. All right. Any we're still taking questions. Any other questions? Okay. I think we did have one example left we were working on in 17.3. This is similar, actually. This is kind of lame now in retrospect. This is easier than the one we just did. But I don't know. I guess I should say it's easier if you recognize what it's telling you. So this is another one. It's from that same section, isn't it? No, it's not. It's one up here. I feel like Rudy asked about one of these. So it's about using the fundamental theorem of calculus. Yeah, we did 39, right? So this is 41. Verify that the fundamental theorem of line integrals can be used, and then evaluate the line integral using the theorem. So verifying that it can be used, the field must be conservative. So I'm going to pose this to you. I want you to think about this. How do you show F is conservative? And then you can you maybe raise your hand? Remember the there's a raise your hand button, right? So I'll give you like 15 seconds to think about it, and I'd love for somebody to explain, how do we show this? Because this is I like what Daniel said. They're like, okay, on an exam, what would I have to show? So how would you show this on an exam? So I'll give you 15 seconds to think about it, and then maybe do the raise your hand button if you want to type in the chat the answer, or just unmute yourself. All right. Anyone ready? Anyone want to explain how you would show that? And this is really this is kind of a general question about how do you, like in general, how do you show that a field is conservative? So it's a little bit different in this particular problem. How about this? Because then, can anyone remind us what the definition is for a conservative field? So related question, what does it mean for a field to be conservative? Does anybody know that one? I actually know you do, because we were just talking about it. All right, these are the tests. So it just seems a little weird in this context, but we have these tests where it's conservative if those cross partials are equal, right? Michael typed it in there. If the partial derivative of f with respect to y is equal to the partial derivative of g with respect to x, right? The problem is, it seems like we can't test that here. So we would say here the partial derivative of f with respect to y is that equal to the partial derivative of g with respect to x. The key is the second question. What does it mean for a field to be conservative? Conservative field means it is the gradient of some function phi. That's what it means to be conservative. Well, our field is a gradient. It's what it is. so this one actually, I feel like it looks hard because it has the gradient in there. But this one is actually easier because it gave you the fact that it was a gradient. Whoa, whoa. So then the field is definitely conservative. It is definitely conservative. Well, this implies then that the line integral can equal just phi at b. Actually, we know them, right? Phi at natural log of 2 comma 2 pi minus phi at 0, 0. But we need to get a phi. We don't know that they're going to be 0, though, Michael. We don't know that they're going to be 0. In fact, they're not here. But it's okay. It's not a closed curve. This one's not closed. You see, it's not closed. It doesn't start and end at the same point. You can even check phi. We don't have a phi yet, though. Maybe we do, but it's not obvious that we do. But you'll see that they're not going to be the same. It doesn't start and end at the same point. So we need to get a phi. But what I'm hinting at here is we have a phi. Do you see what it is? The logic in red is the key. The field is conservative if the field is the gradient of some phi. But our field is a gradient. So what's phi?
Isn't it just the integral of our field?
Good thought. You're making it too complicated, but I understand.
Isn't
No,
it
go ahead.
just e to the negative x cosine y?
It is, because that is the function that we're taking the gradient of. So that is phi. Gradient of e to the negative x cosine of y is the gradient of phi. So that means that thing inside there is the phi. So all we need to do is just do e to the negative natural log of 2 cosine of 2 pi minus e to the negative 0 times cosine of 0. Move this over here. I don't know why when I'm writing on a computer and I have all this space, I still clutter it up. My apologies. But that's the key. So they actually gave us the phi. And they gave the fact that our field was the gradient of a function. So it's conservative. And they gave me the phi. All I need to do is evaluate the phi at the endpoints. This is 1/2. I'll let you think about why that's true. Cosine of 2 pi is 1. E to the 0 is 1. Cosine of 0 is 1. And so we get negative 1/2. So I think I misspoke. Like I'm looking at them like, oh, this one's even easier. Well, to me, I always think about these. It's like, I remember at my old house, there was like my back lock, the door handle was like loose, and it would like, kept like locking, and then like you couldn't unlock. It was really weird. It was like not right. Something wasn't right. So I called this locksmith over to see if he can help with it. He looks at it and he's like, well, whoever installed it put it on sideways, like turned 90 degrees. Oh, And he spent like 5 minutes and fixed it. And it was a super easy fix. But for me, it was not easy because I didn't know what was wrong. I didn't understand it. So that's kind of like this. Like I look at this and say, oh, well, it's conservative because they told me it was a gradient. And then I already have the phi. I just evaluate the phi at the endpoint. So for me, it's easy. But that's a lot of logic that I'm using there that you're still learning. So it's a problem that doesn't require a lot of work, but is not really easy. It's actually not. It doesn't require a lot of work, but it requires really knowledge of the meaning of what is a conservative field, what is a line integral, when can I use the fundamental theorem. So it requires a really high level of knowledge. It's like the one that Daniel saw that insight to, the homework question. It's the same one. Like it's an easy question if you know how to check if a field is conservative, and if you know that on a closed curve, the integral of a conservative field will be 0. But those are big ifs. So some of these, the more you really understand in depth about the theorems we're learning, the definitions, the more you understand those, then problems become simpler. There's not a lot that we can just grind out on these.
I'm kind of confused why it's -1/2, because isn't e to the negative ln 2 -2?
Mm,
And then it's,
no, there's
oh
no,
yeah, never mind. I got it.
it's all good. Yeah, it's all good. Yeah, you're good. Cool. Any other questions on that one? All right, I think I want to just stop here. I was going to do 7.4 or 17.4 today, but I think what we'll do is, I did post those videos, but I didn't post them until this morning. So I think I'm going to ask you to watch 17.4 for tomorrow, and then I'll get 17.5 posted. I'm going to work on that later tonight, and I'll get that one posted. So tomorrow we can do more homework questions, and then we'll practice with Green's theorem. Green's theorem is actually really cool. I can show it to you quickly here in the notes. Green's theorem. I had to change to green backgrounds just for to honor the section name. But what it is maybe I'll just write it down on the page we were working on. Sorry, probably easier just to do that. So Green's theorem. Oops, I'm still in red. Says if we have a closed curve and we want to find the line integral along that closed curve. So these are usually not on conservative fields because it would just be 0 then. What you can do instead is you can do a double integral over the region of what's inside of the partial derivative of g with respect to x minus the partial derivative of f with respect to y. I always want to double check and make sure I got those right here. Yeah, partial derivative of g with respect to x minus the partial derivative of f with respect to y. What that's basically saying is the line integral is the circulation, and it's the circulation in the counterclockwise direction. The circulation, if you recall, is how much of the field is pointing in the direction. It's kind of like Max's earlier question about work. So the circulation gives you like the total work around the edge. And then you're like, well, what is this thing inside? What you're doing there is you're basically calculating the rotation of the field inside. It's called the curl. You're finding the total curl inside. And those two are equal. So you can either find the line integral outside and get the total work outside, the total circulation, or you can do a double integral inside. And so either one will do. And so this is kind of like another one of these two different things that are equal, and which one you choose depends on the context. And sometimes this is where I might ask you to verify Green's theorem on the final. say you'd have to show me that it would work, and then you'd have to find the line integral and also find the double integral and show that they're equal to each other. So we'll do an example of that one. We'll do an example of that in class tomorrow, and then we'll talk a little bit about 17.5 if we have time. And then, yeah, Thursday will be review day, and then exam will be posted after class on Thursday. All right, I think I'm going to stop here for today. Any last questions before we sign out?
Yeah, this might be a big question. Why is the circulation counterclockwise?
That's a good question. I don't think I have a great answer off the top of my head about why it is that way. I'd have to think about it because I don't think we talked about it in the derivation either. There's a video that I linked that I didn't really prove the theorem here, but you'll see like all of the arrows here, they're always that way. Maybe I'd have to think about, let's go back to the definition of circulation because it seems arbitrary. Why not clockwise? You know, why counterclockwise? So let's go to circulation. It was at the end of 17.2, I believe. Right, so this one doesn't give a direction. And then for our closed one, it's counterclockwise. So why is it, I wonder if it's just chosen. Because you have to pick one. You know what I think it is? Hold on, I don't know, I'm going to a different tab. Sorry, I think that's why. So I think it has to do with the fact that this gx minus fy, if you'll see in the notes, I'll talk about why, if that's positive, it means it's a rotation in this direction. This is the reason why, I remember now. So there's in the notes, I try to give a little demonstration about why it's positive, why the rotation is positive. It's right in the middle here. This is the meaning about why, if that curl is positive, it's giving you a rotation in that direction. So then what they do is they say, well, let's make the circulation match and make the circulation positive, and so following it in that same orientation. So I think the reason it's counterclockwise is because of this, because of choosing to do it in that order. We could switch the order and then go clockwise. Yeah, so Green's theorem just chooses to do it in that order, and then it forces us to be counterclockwise. Yeah, it's a good thought, good question. All right, I'm gonna sign out for today. I'll post a recording later, which doesn't matter for you because you're already here. But yeah, that's it. And I will see you tomorrow for some 17.4 and some more homework questions. All right, take care, everybody.